Hey guys, in this particular video I'm going to cover a much more advanced problem which utilizes the mechanical energy formula we derived earlier. So this is our problem. Let's say that we've got a roof just here, and let's say that we've got a spring which is being unstretched, hovering downwards. So this is unstretched at this point, there's no force. And let's say that the unstretched length of this spring is a distance d, and let's say that we decide to attach a block to this spring. So this is our block right here. We decide to attach a block to this spring, and then we make the block slide down a frictionless circular path until the block ends just here. And my question to you is, what is the velocity of this block as it finishes its slide? Just as it finishes this circular path slide, what is the velocity of this block? Right? And in order to do this, we need to know a few things. First of all, we need to know the radius of our particular slide. We need to know that this distance right here, I'll leave it in very generalized. I'll leave it as very generalized. So this distance I'll just call capital R, denoting the radius of our circle. Right? So basically we've attached a block to this unstretched spring, and then we're dropping the block and watching it slide. It's not rotating, it's sliding down this block, down this path in a circular type of path, and then just as it gets here, what is the block's velocity? And remember that at all times the block will be connected to the spring. Right? So in which case, in this final position, you'll be having a very, very, very stretched spring like this. Very stretched, pointing to the block just there. Alright, well, I don't want to clutter things up, so I'll just delete that. But essentially, this thing is connected to the spring, and I want to find out what its velocity is. And we can do this using Newton's laws. We can do something like that, but it's much easier, and I think you'll find, to apply this particular formula. The change in mechanical energy is equal to the work done by non-conservative forces. So what's our first step in any dynamics problem? That's right, to create a free body diagram. So let's do that. Let's create a free body diagram of our block sometime mid-flight. So this is our block right here, sometime mid-flight. Right? What are going to be the forces acting on this block? Well, you're going to have a force due to gravity acting directly downwards, as always, with the magnitude mg. You'll have a normal force acting perpendicular to the path, as always, n. Anything else? Well, yeah, you'll have a force due to the spring acting roughly in this direction, right? I mean, if you were to draw it, it would look, this would be the spring right here, right? So you'll be having a force due to the spring acting in that direction. It wouldn't be exactly vertical, but it would be almost vertical based off where I've drawn it. Alright, well, let's see if we can figure out how to apply this free body diagram to this particular equation. What are our conservative forces and what are our non-conservative forces? Remember, this is our force due to our spring, so that's going to be kx, right? So, what are our non-conservative forces? Well, the only non-conservative force acting in this free body diagram is our normal force, right here. Right? Because we know that our force due to gravity is conservative, and we know our force due to our spring is conservative. So what's the work done by our normal force, right? So this is just going to be our work done by our normal force. Right, well, if you'll recall that work can only be done by a force if the object moves in the direction of that force, right? I mean, I definitely recommend you look up my videos on work to remind yourself of that. But essentially, the work done by the normal force can only be done if the object moves in the direction of the force. But notice, at every single point of this, object is at, the object will be moving perpendicular to the force. In other words, this normal force will never ever do any work whatsoever. So this normal force is going to be equal to 0. Right? You can do the maths to prove it, but your intuition should be enough to verify this, that the work done by your normal force is going to be equal to 0. Alright, well, let's just leave the left-hand side where it is for the moment. Alright, and now let's expand it. So what's your what's your change in mechanical energy? That's going to be your change in kinetic energy plus your change in potential energy, which is your change in gravitational potential energy, plus your change in elastic energy. Alright, now a few things to point out. First of all, this block isn't rotating, right? So we use our standard kinetic energy formula, a half mv squared, right? We don't need to concern ourselves with rotation at this point, although we will in later videos. And another thing, I'm not sure if I mentioned it earlier, but this spring was initially unstretched, meaning that our equilibrium position is D, right? So in order to figure out this term, we need to figure out the amount the spring has stretched at its final position here. Let's call this our final position 2, and let's call this our initial position 1. Right? But we'll cross that bridge when we come to it. For now, let's just expand out our formula. Right? What's our change in kinetic energy? That's going to be a half times m, the mass of our block, times by our speed at our second point. We don't know what that is, so we'll leave that as v2 squared, minus v1 squared, right? What about our gravitational potential energy? Well, our change in gravitational energy will just be mg y2 minus y1. Right? What about our elastic energy? Our change in elastic energy is going to be a half k, our spring constant k. I probably should have drawn that up here. Our spring has a spring constant k, right? Times by x2 squared minus x1 squared, right? And I really want, a lot of students get really confused here because they think x2 has something to do with the x direction. It's very confusing notation. Basically, x2 denotes the amount the spring has stretched to get to its second position, and x1 denotes the amount of distance that the spring has stretched to move it to its first position, right? All right, well, let's plug in values. What do we know? Well, we know that v1, assuming we connect the object just here and drop it, it's going to be equal to 0. It starts at rest, right? We've just dropped it, right? v2 is what we're trying to find, so we'll leave that as a question mark for now. What about y1 and y2? Right? Well, it depends on where we place our axis. For simplicity's sake, I'm going to place my axis right here. Although we didn't have to, we could place it anywhere. So I'll call this x and I'll call this y. Right? In other words, y1 is just going to be a vertical distance r above the origin, right? I mean, this distance right here is a distance r, right? I mean, if this is a circle, it must be. Right? So this distance is a distance r because it travels in a circle, meaning that y1 is going to be equal to r. Right? What about y2? Well, based off where I place my axis, y2 is going to be equal to 0. What about x1? Remember, I assumed that the spring was initially unstretched when we connected our block to it, meaning that x1 it's not going to be equal to d. It's going to be equal to 0, right? Because remember, x1 denotes the amount the spring has stretched from its equilibrium position, which is 0 in this case, right? It's not going to be d. What about x2? Now this is an interesting case. We'll have to use Pythagoras to work out what x2 is. And essentially what x2 is, it's this distance right here. Let me just redraw that really stretched string again. It's this distance here minus our equilibrium distance d. And let me show you that by drawing another simple example here. Alright, so this, let me just draw a more simplified version of what we've got. This is our distance we're interested in. This is our hypotenuse of our triangle. This is our path right here. This is our path. Initially vertical, and then curved. And then curved. Right? But if we were to draw this imaginary line going vertically downwards, we can create a triangle here and use Pythagoras to work out what this hypotenuse distance is right here. That'll have to do. Alright. Well, we know that this distance here is going to be our distance r, our radius of our circle, plus our distance d, right? That's this distance right here. That's this distance right here to here. That's going to be r plus d. I hope that makes sense. What about this distance here? What about this distance just here? From here to there. Well, because it's a circle, that's just going to be a distance r, right? So this side of our triangle is just going to be a distance r. So what's this hypotenuse? Well, we can work that out. That's just going to be, remember, a squared plus b squared equals c squared. That's just going to be equal to the square root of r plus d squared plus r squared, right? So in other words, the total distance of our spring now, not the amount it's been stretched, but the total distance of our spring from this point to our final point 2 is going to be equal to this funky square root sign. It's going to be equal to this, right? So what's the amount that the spring has been stretched? Now this is the tricky thing. This is what stumps students all the time. The amount of distance that the spring has been stretched is going to be equal to the total distance of the spring, which is r plus d squared plus r squared, minus its equilibrium position, d. That's going to be huge. That's the kicker. That's what all students fall for. All right, these are our conditions right here, which we can sub into our equation. All right, I hope that makes sense, guys. Let's see if we can evaluate our expression a little bit more, noticing that this entire expression is going to be equal to 0. All right, well, let me write it out. That'll be, let me just write out the right-hand side first. That'll be a half times by your mass of your block times by v2 squared. We don't know what that is, so I'll leave it as v2 squared, minus v1 squared, which is 0 squared, plus mg times by y2 minus y1, which is 0 minus r, plus a half k, our spring constant, times by x2 squared minus x1 squared. What's x2 squared? Well, there's no easy way to simplify it, but it'll just be r plus d squared plus r squared minus d. And that's going to be squared minus x1 squared, and x1 is 0, so that's just going to be 0 squared, is going to be equal to 0, right? Alright, well, let's see if we can simplify this a little bit more. I'm going to do this in one step because I'm fairly sure by now we're all familiar with algebra. So I'm just going to bring v2 to the, I'm going to bring all other terms to the right-hand side. I'm going to leave v2 where it is. So that'll be a half m v2 squared is going to be equal to mgr minus a half k times by this very, very convoluted square root sign, r plus d squared minus r squared, plus r squared minus d. That's going to be squared. Alright, well, let's see if we can simplify this a little bit more. If we times by 2 and then divide by m, then we're left with v2 is going to be equal to 2gr. Actually, I'll do the intermediate step. I'll leave that as a squared just there. So I've multiplied it by 2 and divided by m. So 2gr minus k on m times by whatever this beast is. It's going to be the square root. It's a little bit laborious writing this out every time. R plus d squared plus r squared. I could simplify that middle bit if I wanted to, but I won't. Minus d squared. Alright, and rather than rewriting this all again, I can square root both sides and be left with this. Alright, that's our answer. This is a generalized solution to our problem, right? So in other words, the magnitude of our velocity will always be equal to this right-hand side equation just here. Alright, I hope that makes sense, guys. If you wanted a more specific type of problem, all I need to do is give you particular values. I could say k is equal to a certain value, I could say d is equal to a certain value, r, etc., and then you'll be able to solve it by literally plugging into this formula. But for now, I think it's really useful to get used to generalizing solutions because we're going to be doing it a whole lot. Anyway, I hope that makes sense, guys. I might give one much harder example just to hammer in this, hammer into how to solve these particular issues, and then I'll move on to a different topic.